In this video, we're going to talk about maximum values and minimum values of functions. Note that the plural of maximum is maxima, and the plural of minimum is minima. So we're going to start with four important definitions that are related to each other. The first one is we say that if we have a number c, which is in the domain of a function f, then we call that f of c to be the absolute maximum of f on D, provided that f of c is larger than or equal to any other function value in the domain of x. Graphically, we would think of the absolute maximum as being the y-coordinate of the highest point on the graph of f. And if you have an absolute maximum, you might have an absolute minimum. It's a similar definition. We have a function value, f of c, where f of c is smaller than or equal to any other function value of x, where x is in the domain of D. Graphically, that would be the y-coordinate of the lowest point on the graph, if it has a lowest point. So absolute max and absolute min, sometimes we would say global max or global min. Those phrases are synonymous with each other. Now you may have a point on the graph where it is not the absolute highest, but it's higher than all of the points around it. And we would call the y-coordinate of that point a local maximum. So f of c is a local maximum, provided that f of c is larger than any function value around it whenever x is near c. We'll talk more about that in a minute. And if you have a local max, you may also have a local min. That would mean that the function value, the y-coordinate, is smaller than all of the y-coordinates around it, but might not be the absolute smallest. So instead of saying local min or local max, we may use the phrase relative max or relative min. So let's make some important notes here. First of all, whether we're talking about absolute or local or max or min, these are all numbers. They're all y-coordinates of points. They're not points, so we should be careful about that. They don't have x-coordinates, they don't have y-coordinates, they are just numbers. They correspond to y-coordinates, but they're just numbers, not ordered pairs. And when we're considering a local max or a local min, we have that phrase whenever x is near c. So that really means when x is an open interval containing c. So that tells us that c has to be in the interior of the domain of f. There must be points to the left of c and to the right of c. Otherwise, it's not in the interior. You can't put an open interval around it. There has to be that little bit of space to the left and a little bit of space to the right. Otherwise, it's not on the interior. And so if you don't have numbers to the left of C, or if you don't have numbers to the right of C, then you cannot have a local max or a local min at x equals C. So for example, if you're at the end point of a closed interval, You cannot have a local max or a local min there, which is a little bit odd because you can have an absolute max or an absolute min. So you might find yourself in a situation where a number, f of c, could be an absolute maximum without being a local maximum. So that's a little counterintuitive, but that's what the definition tells us. So let's look at a couple of examples. Here we have a constant function, f of x equals 1. Since it always has the same function value, the same y coordinate, then that one y coordinate, the number 1, is an absolute max. It's also an absolute min. It's also a local max. It's also a local min. Kind of boring. Let's take a look at f of x equals absolute value of x. Now, from looking at this, we can see that, oh, we definitely have a low point. So f of 0 is an absolute min, and it's also a local min. There are numbers to the left and to the right of it. But there is no absolute max because the function continues to grow without bound, and there's actually no local max either. Here's another example, which is piecewise defined, just made up of line segments. So we can see that f of 3 is the highest point overall. It's an absolute max, but it can't be a local max because there's no points to the right of it. And f of 0 is an absolute min, but it's not a local min. Here at x equals 1, f of 1 equals 2 is a local max. And at x equals 2, f of 2, which equals 1, is a local min. All right, here we have another piecewise defined function. And this function is defined for all values from 1 to 5, including 1, but not including 5. So the high point here is an absolute max, but it's not a local max. We do have a local max when x equals 3. Whether I go to the left or to the right, if I don't go too far to the left, that the y coordinate of when x equals 3 is going to be larger than any of the y coordinates close to it. Now, f of 4, which is 2, that is a local min, and there is no absolute min. Why is that? Well, the open circle down here is telling me that the function, when we come from the left, even though the limit as x approaches 3 from the left is 1, there's always going to be at numbers that get closer to 3 that are always going to get arbitrarily close to 1 but never equal 1. So you can't say that 1 is a absolute min because the function, there is no x value where f of x equals 1. F of 3 jumps up to be 3. So that situation is odd because we have that jump discontinuity. And so our next video, we're going to see when we have a continuous function, things are more intuitive and they make more sense.